Hello everyone. Okay, we meet again. Okay, for the last chapter of term 2. Okay, which is transition element. Alright. Okay, actually for transition element, okay, we only focus on the first 10 of transition element. Alright, starting from scandium until zinc. Okay, so I will start by explaining the physical properties of transition element. Okay, here is the mind map for the overall physical properties. Alright, basically I divide the transition element into 4 parts. Okay, the first part is physical properties. It contains about similarities between the elements, and then variation in successive ionization energies and comparison it with S-block metal. Okay, alright, the second one is chemical properties. Okay, in chemical properties, we will learn about variable stabilities, oxidation states, complex ion formation, valent ion, and catalysis. Okay, the third one is complex ion. Right, in complex ion, we will learn about nomenclature, bondings, type of ligand. Okay, the last one is uses. Alright, okay, so for physical properties, I will show for this part, which is electronic configuration of transition element. Alright, so for general electronic configuration, our first transition series, is 3dx, 4s2 or 4s1. Okay, 3dx, x represent 1 until 10. Alright, so for the balanced electronic configuration, of first transition series is 3d, x, 4s2. Alright, okay, now let's take a look the video. Okay, let's take a look the video. Okay, so I want to show you how to compare in filling the electron in orbital of calcium and titanium. Okay, so for calcium, calcium have 20 proton number, so we map it up. Okay, followed by energy level. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 11, 12, 13, 14, 15, 16, 17, and 18. So this is the 18. Okay, and then 18. Okay, this one is 80, 90, and 20. Okay, so this is the electronic configuration for calcium, which is it's only consists of 1s until 3p and 4s only, not included the 3d, so it no need to fill up the 3d. So for calcium, it have empty 3d. Okay, so that's why we will write it like, for that one is the argon, so this is the argon part. So this is the argon part. Okay, so this is the argon part, and then followed by 4s2. That's why calcium is located in S block. Okay, for titanium, let's fill up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Alright, 18. Okay, 18. Okay, 19, 20, and 21, and 22. Okay, what happened is, it will automatically, when the 3d orbital is filled up by electron, automatically it will become lower energy than 4s. So that's why, when we write the electronic configuration of titanium or other transition element, so we will write down like this. So this one is argon, 18. So argon, and then followed by 3d2, and then 4s2. So this is the electronic configuration of titanium, which is transition element. Okay, here is the all the electronic configuration of the first transition element, starting from scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Right. Okay, so here is the electronic configuration of the all elements. Okay, now we take a look how to write the orbital diagram of the transition element.
Okay class, so here is the electronic configuration of transition element, okay, which is here is the shortened electronic configuration. Okay, while this is the valence electronic configuration of transition element, which is transition element is a D block. So this is the valence electron configuration, but I wrote in a orbital diagram. Okay, how to write the orbital diagram, okay, of transition element? Okay, take a look for the scandium. Scandium is a 21, so 18. Okay, 18 of argon, so 18. Okay, and then followed by 4s orbital. Okay, 18, 19, 20, and 21. So we must fill up in a 4s orbital first, followed by 3d, because 4s is a lower energy level compared to 3d. So you must memorize the principle in writing the electronic configuration. We have Hans rule, we have Aufbau principle, okay, we have Pauli exclusion. Okay, and then okay, for titanium we have 22, so 18, 19, 20, and 21, 22. Okay, so here is the valence electron, which is 3d2 and 4s2. Okay, followed by vanadium. Vanadium have 23 proton number, so 18 is from argon, so 18, 19, 20. Okay, and then 21, 22, 23. So we have 3d3 and 4s2 of valence electron configuration of vanadium. Alright, so followed by chromium. Alright, so for chromium is a special one because okay, if you can see that it have 3d5 and 4s1. Okay, so we have 3d5, so 18. Okay, 18 from argon, 18, 19. Okay, and then 20, 21, 22, 23, and 24 of chromium. Okay, why this is the special one? Because okay, 3d5 and 4s1 is more stable than 3d4 and 4s2. Okay, which is the half field orbital is more stable than partially filled. Right, this one is you must memorize lah. Okay, for chromium. Okay, for chromium. Okay, and then for iron. Okay, for manganese and iron, okay, the same steps. Okay, which is we have 25, okay, 18, 20, 19 and 20, 21, 22, 23, 24, 25. So for manganese, okay, for manganese we have 3d5 and 4s2. Okay, for iron 26. Okay, it have 18 for argon, 18, okay, 19, 20, 21, 22, 23, 24, 25, and 26. So for valence electronic configuration for iron is 3d6 and 4s2. Okay, so you can write down all the orbital diagram, okay, until zinc. Okay, we take a look for copper. Copper is also special because its electronic configuration is 3d10 for S1. Alright, so 18, okay, 90, okay, 20, 21, 22, 23, 24, 25, 26, 27, 28, and 29. So for copper, it have 3d10 and for S1, which is this electronic configuration is more stable than 3d9 and 4s2, okay, which is this fully filled orbital. Okay, this fully filled orbital, okay, is more stable than partially filled orbital, which is 3d10 is more stable than partially filled of 3d9 orbital. Okay, so for chromium and copper, okay, it have different electronic configuration, okay, because for chromium the half field orbital is more stable. Okay, because for chromium the half field orbital is more stable compared to partially filled. Okay, while for copper, okay, the fully filled orbital is more stable than partially filled orbital. Okay, for zinc, it has 30 proton number. So in order to write the electronic configuration, so it has 18 for argon, 90, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. Okay, so for zinc, it have 3d10, and for S, 2.
Okay, among the all transition element here, right, they have a two element, okay, which is different from the others, right? So for chromium and copper, okay, in writing the electronic configuration, they didn't follow the three principle because of their stability. Okay, if you can see that for chromium, right, it's 3d5, and for S1 is more stable than 3d4 and for S2, which is this 3d5 is halfway orbital, which is more stable than partially filled orbital of 3d4. Alright, and then for the second element, which is copper, which has 3d10 and for S1 is more stable, okay, than 3d9 and for S2, okay, which is this 3d10, okay, is a fully filled orbital, okay, and it's more stable compared to the partially filled of 3d9 orbital. So actually for these two kind of element, you already learned in term 2. Okay, now let me show you how to write the electronic configuration.
Okay, in writing the valence electronic configuration of chromium, okay, suppose, okay, that we must fill up in a for S orbital first, followed by 3d orbital. Alright, so chromium, so let's say it have 18 for argon, and then 18, 19, and 20, 21, 22, 23, and 24. Okay, suppose this is how we fill up the electronic configuration, but this condition is less stable. Alright, so that's why for chromium we fill up like this, okay, for S1 and 3d5, because this halfway orbital, okay, which is 3d5, okay, is more stable, okay, compared to 3d4 orbital, which is partially filled orbital, is less stable. Okay, why the halfway orbital is more stable? So that's why in order to write the chromium orbital, okay, so we must draw like this. So this is the correct one. Okay, so we can see that 3d5 and 4s1 is more stable, okay, then 3d4 and 4s2.
Okay, let me see the definition of transition element. Okay, so what is transition element? Okay, transition element is the element that forms at least a stable simple ion with incomplete or partially filled d orbital. Alright, so refer to the electronic configuration here. Okay, we can see that for scandium, okay, and zinc are not transition element. Okay, why this is happen? Alright, okay, we take a look the electronic configuration for scandium. It has 3d1 4s2. Okay, in order to form scandium 3+, so it will remove the 3 outer electron. Okay, which is when we remove the outer electron starting from 4s2 and 3d1, so left is 18, which is argon, represent the 18 electron. So we can see for 3d subshell for scandium ion is empty. So this didn't follow the definition of transition element, okay, which is it must incomplete or partially fill the orbital when it forms simple ion. So for scandium, it is not a transition element because for scandium 3+, it has empty 3d orbital. Okay, for zinc, okay, zinc has a 3d10 and 4s2 orbital. Alright, okay, while in order to form zinc 2+, Okay, it will remove the first 2 electron from 4s2. So finally, okay, it left as a 3d10. And once again, so this 3d10 is a fully 3d subshell. So it's not obey the definition of transition element, which is incomplete or partially filled d orbital. So that's why for these both are not considered as a transition element. Alright. Okay, let's see how to write the electronic configuration.
Refer to this electronic configuration. Okay, why scandium and zinc are not a part of transition element. Okay, now we refer to the scandium electronic configuration. Okay, when scandium, it form scandium ion, which is scandium 3+, which is it will remove 3 outer electron. Okay, for the first one, it will remove the outer one, which is 4s, electron in a 4s orbital. So 1, 2, and 3 to be removed. Okay, and finally, okay, for scandium 3+, scandium ion, then it will left as a 3d0 and also 4s0. So this is not obey the definition of transition element, which is, okay, this transition element must form at least a stable simple ion with incomplete, and partially filled of d orbital. So okay, while for scandium it has 0 electron in the d orbital. Okay, for zinc, okay, why zinc is not a part of transition element? Okay, we take a look when zinc want to form zinc 2+. Alright, so it will remove the outer 2 electron, okay, which is we remove from 4s orbital 1 and 2 here. So what we form is it will left as a 3d10, okay, which is all the electron in 3d orbital are fully filled. Okay, 3d orbital is a fully filled. Okay, while the definition of transition element, that transition element must form at least a stable simple ion with incomplete or partially filled of d orbital. Okay, while for scandium it have 0 electron, and for zinc 2+, it have fully filled electron. Okay, it have fully filled orbital in 3d orbital. Right, that's why these two element we not consider as a transition element. Right, so for scandium, okay, and zinc, it's not a part of transition element.
Okay, now let's see this part. Okay, actually, okay, when transition metal form ions, okay, electron lost first from 4s subshell rather than 3d subshell. Alright, if you can see that from energy level diagram, okay, the 3d orbital is a higher energy compared to 4s orbital. Alright, so energies, okay, of 3d and 4s orbital are relatively close. So it close each other. Okay, and then the 4s level is energetically more stable, okay, than the empty 3d level. So 4s is more stable. Alright, so 3d is the less stable. So the higher the energy level, okay, the less stable. Alright, however, when the 3d orbital is occupied by electron, so the 4s electron are repelled further from the nucleus to a higher energy level. Okay, this 4s orbital will go further, so it will become higher energy level than 3d orbital. Alright. Okay, consequently, okay, when forming ions, okay, so electron from higher energy 4s level are lost, okay, before 3d level. So that means that electron in 4s orbital, okay, we remove first followed by 3d. Alright, so information of cobalt 2+, alright, we already remove the outer electron in 4s orbital, so 3d 7 Nah.